People repeatedly insist that it's basically a fact, proven by quantum mechanics, that we live in a multiverse. In fact, even some academics spread this viewpoint on social media platforms such as YouTube, and it has become rather popular there. The people who push this narrative on social media platforms usually claim it is the simplest and most reasonable viewpoint of the natural world based on our best scientific theory of nature, therefore we should just accept the multiverse as reasonable. The many worlds interpretation is in fact more complicated than traditional quantum mechanics and entirely incoherent. Whatever you have been told about the supposed reasonableness of the many worlds interpretation, even sadly by people with a real education who should know better, is just patently false. The many worlds theory suggests that every possible outcome of a quantum event happens, creating a vast number of parallel universes. But hold on, just because it's a fascinating idea doesn't make it true. The theory is far from being a proven fact. In reality, it's one interpretation among many in the complex world of quantum mechanics, and it's not even the simplest one. Traditional quantum mechanics, with its wave functions and probabilities, remains a robust and less convoluted explanation of the quantum world. So, while the many worlds theory makes for great science fiction, it's important to remember that it's just that, fiction. The universe is already a marvelous place without needing to split it into countless parallel realities. Question everything, and don't just accept a theory because it sounds cool or because someone with a degree says it's true. In quantum mechanics, you compute the motion of particles using the Schrödinger equation, whereby they evolve not as point-like particles but like waves, up until you go to make a measurement. At the moment of measurement, you then square the wave to get a probability distribution of where the particle will end up once you measure it. This final step is known as the Born rule. There is a sudden jump of the wave function when you make a measurement. There are two separate problems here that should be separated to avoid confusion. They will point out that the jump caused by measurement is arbitrary because, well, what is a measurement? Why should big objects like measuring devices even play a role in a fundamental theory of nature? John Bell had made similar criticisms. While this is indeed a legitimate criticism of the Copenhagen Interpretation, it turns out it is hardly a big deal at all, because you can simply replace measurement with interaction and you do not run into any inconsistencies. You do not need to posit a whole multiverse to get rid of the reference to measurement in quantum mechanics. Simply replacing measurement with interaction gets you into the relational interpretation, which many worlds interpretations proponents seem to act like simply does not exist. There are two problems here, not just one. The other problem is the discontinuous nature of quantum mechanics. The fact that there is linear evolution according to the Schrödinger equation that seems to jump to something non-linear at the moment of an interaction predicted by the Born rule. By treating measurement as merely an interaction like any others, the relational interpretation expands the discontinuity even further. Every interaction has a discontinuous jump. Is this a problem? Why is this a problem? Why can this not just be how nature works? There is no problem with saying that particle motion is mathematically discontinuous. There is no contradiction in the mathematics, nor any philosophical issues making it coherent. The distaste for it is clearly an argument from some arbitrary notion of mathematical beauty rather than a deep philosophical problem in the theory. Indeed, quantum mechanics had actually been formulated by Werner Heisenberg using matrix transformations prior to Erwin Schrödinger deriving his famous equation. They are mathematically equivalent, but Schrödinger too chose to promote his formulation instead of other formulations partially because he found the discontinuity in them to be ugly. Yet even Schrödinger had come to reconsider this position when he realized that he simply kicked the can down the road, so to speak. The discontinuity he removed in Heisenberg's formulation between interactions was shifted to the moment of measurement. No longer were there jumps from interaction to interaction, but there was now a jump between the wave formulation described by the Schrödinger wave equation and its discontinuous collapse into a particle when measured. There seems to be a fundamental discontinuity in quantum mechanics that is impossible to get rid of. If you claim particles do not hop like fleas between interactions, then you end up just shifting this discontinuity to the moment of measurement, observation. If you remove it in one place, it just shows up elsewhere. MWI proponents are a continuation of this mindset. They, just like Schrödinger, desperately desire to restore the poetry of continuous evolution. For decades, the idea that consciousness plays a crucial role in the measurement process has intrigued both scientists and philosophers. This notion primarily stems from the Copenhagen Interpretation, which suggests that a particle's wave function collapses into a definite state only upon observation. But what does observation really mean? Is it the act of a conscious being looking at the particle? Or is it simply any form of interaction, as we've discussed earlier? One of the most intriguing ideas is the observer effect, which posits that the mere act of observing a phenomenon inevitably changes that phenomenon. This concept has been popularized in various forms of media and has even seeped into popular culture, often leading to the misconception that human consciousness alone can alter the physical world. However, in the realm of quantum mechanics, observation doesn't necessarily imply human consciousness. Instead, it's about any interaction that causes the wave function to collapse. This could be a measuring device, another particle, or any form of interaction that essentially locks in a particle's state. Yet the idea of consciousness having a special role in quantum mechanics isn't entirely dismissed. Some interpretations, like the von Neumann-Wigner interpretation, argue that consciousness is indeed responsible for the collapse of the wave function. This interpretation has fascinated many, although it remains highly controversial and lacks empirical evidence. However, when it comes to the many worlds interpretation, things get a bit more intricate. Accordingly, every possible outcome of a quantum measurement actually occurs in some branch of the universe. But how do we reconcile this with the Born rule, which assigns specific probabilities to different outcomes? An intuitive answer may be to just assign equal probabilities to all possible outcomes. Since there are two possible outcomes, then you assign each an equal probability of 50%. If you assign each branch of this multiverse equivalent probabilities, then you get the wrong answer. Clearly, this simple self-location cannot work. Indeed, there is no simple way to reproduce the predictions of the Born rule. Yet, this is just patently untrue. If you discard the Born rule as an assumption, it is simply impossible to then derive the Born rule without some sort of different assumptions. There is yet another major issue with the many worlds interpretation. Even if we accept that it is more complicated than other interpretations of quantum mechanics, it at least is coherent, yes? So it is not that unreasonable to believe in it. In quantum mechanics, the evolution of the Schrödinger equation is used to predict where particles will be found. The wave equation itself was discovered by analyzing the behavior of particles and is applicable to all particles. We only need the evolving waves. Yet again, the evolving wave is not visible. It is a purely mathematical construct used to predict together how visible particles move. If you just have the wave, then how do you derive the wave in the first place? Even worse, the Schrödinger equation is applicable to all particles. So what MWI proponents argue is that everything is merely the invisible waves we use to predict the behavior of visible particles. Nothing else exists besides the invisible waves. This brings us to a crucial point. Without the tangible, observable particles, the entire framework of quantum mechanics loses its grounding. As we peel back the layers of quantum mechanics, it becomes apparent that the many worlds interpretation is just one of many attempts to make sense of the quantum realm. While it struggles with coherence and empirical grounding, other interpretations offer different perspectives, each with its own strengths and weaknesses. One such alternative is the Copenhagen Interpretation, which posits that quantum particles exist in a superposition of states until they are observed, at which point they collapse into a single state. This interpretation emphasizes the role of measurement and observation, and while it avoids the complexity of multiple worlds, it introduces its own set of philosophical quandaries about the nature of reality and observation. Another fascinating contender is the pilot wave theory, or Bohmian mechanics. This interpretation suggests that particles have definite positions at all times, guided by a pilot wave. It revives classical determinism in a non-local fashion, providing a clear ontology but challenging our understanding of locality and causality. The decoherence interpretation, on the other hand, offers a pragmatic approach by explaining the appearance of wave function collapse through the interaction of quantum systems with their environment. Lastly, the relational interpretation proposes that the properties of quantum systems are not absolute, but relative to other systems. This interpretation aligns with the relational nature of space and time in general relativity, offering a harmonious view of the universe, but at the cost of redefining our understanding of objectivity. In the end, quantum mechanics remains a frontier of scientific inquiry, continually challenging our perceptions and inviting us to question the very fabric of existence.